नहीं आएगा। A very good morning to all. On behalf of Shri Shankara Technical Campus, I welcome to all of the participants in the 1-week STTP sponsored program, Multi-Objective Optimization Methods for Engineering and Scientific Applications. It is organized by Department of Mechanical Engineering, SSTC, SGI, Bhilai, and is sponsored by AICT New Delhi. Today, the first speaker is Dr. Akhtar Khan. He is assistant professor in IIIT DM Kurnool. He has obtained his PhD from NIT Rourkela, and his areas of interest is machining of difficult to cut materials, micro and nano machining, cryogenic machining, optimization methods in engineering and design, and multi-criteria decision making MCDM. He has a vast teaching experience. He has published more than 20 national and research papers, international and national research papers, and presently he is serving at IIIT DM Kurnool. Today, Dr. Akhtar Khan will present his expert talk on response surface methodology, RSM. So, and if you have any questions during the presentation, please type them in the question box in your control panel. Will be discussed at the end of the lecture. Now, we will turn the time over to Dr. Akhtar Khan to deliver his expert talk on response surface methodology. Dr. Akhtar Khan, you are welcome. Good.
Thank you, sir. Thank you very much.
Start, sir.
Good morning, sir. Good morning, one and all. Am I audible, sir? Am I audible?
Yes, sir. Yes, sir. You are audible.
Okay. Thank you. Thank you
Yes,
for the
sir.
confirmation. So, a very good morning to one and all. I welcome once again to my second and last session as a part of this short-term training program. So today, as sir has already told, that I'll be discussing on a topic. This is a very vast topic actually, but whatever work I have done during my PhD work from this topic point of view, that is response surface methodology, I'll try to discuss with you, so that based upon your convenient, you can explore it more, or if you find that this much exploration and this much knowledge is sufficient to you to proceed with your existing or current or future work, whatever you are going to plan, so it will be very beneficial to you, and that will be very fruitful for this particular session. So let me first share my screen, and then we'll proceed with today's session. As I told you that response surface methodology is actually very vast topic. So whatever I have done, that part I will try to explain, including some basics or some fundamentals. Please confirm whether my screen is visible or not. If it is visible, I will process. Any one of the participant or organizer, please confirm.
Yes,
whether
sir.
my-
It's visible, sir.
Thank you very much. So, as I told you, we will discuss today response surface methodology. So, as the title of this particular STTP suggests, we are going to learn a number of optimization techniques. So, out of existing optimization techniques, this is one of the most popular optimization technique, response surface methodology, used by various area of engineering science and by researchers and academicians. So it is very popular one. So it is obviously by the name itself suggests that it uses some surface. So from this name or title, we can come to a conclusion that this might be a graphical approach, because surface is nothing but graph actually. So we should say, or we can say, that this particular approach of optimization, because most of the optimization whatever we have learned as a part of this particular course, or including all other existing optimization techniques, most of the techniques are based on some mathematical calculation, are mathematical in nature. But in addition to mathematical in nature, obviously this RSM also is mathematical modeling process basically. But in addition to mathematical modeling, it also represents or it also can be represented in the form of some graphical representation, and then with the help of this graphical representation we have to interpret the graph in order to get the optimal solution. So you might be, I think you might have learned already that what is this optimal solution, in optimal also what is local optimal solution, and what is global optimal solution. So there are a number of techniques which will help you to reach at a local optimal solution, and some other techniques are there, advanced techniques we can say, like soft computing techniques. You might be learning other techniques also. I think as per the schedule I have seen, next is TLBO and other things. So you will also learn soft computing techniques which will help you to reach up to global optimal solution. But to reach at optimal or to reach at a global optimal solution, you need some mathematical model, some mathematical governing equation. So here in this particular method also, it suggests some mathematical equation in the form of empirical model, and with that model what we will do, we will predict the values, and definitely we will have one experimental data. So as all optimization method, and you might have started with DOE, learning DOE, that is design of experiment. So initially in the very first step, before conducting the experiment, you have to design it. So that design part you might have already learned, that is let's say factorial design. So in factorial also you might have learned partial factorial, full factorial, whatever it may be. So one design methodology is this also, that is RSM. So here you will learn how to design the experiment. It will give you an orthogonal array that represents the design of that particular experiment. Once the experiment is designed, you can go for conducting or performing the experiment as per your design provided by this particular method. This method is integrated in different software tools. The popular tools are Minitab, which I am going to use today. I have already used this one only, but other than Minitab, some other tools are also there, like Design Expert. I think expert or some expert. I need to check. The spelling is immaterial. So Design Expert is also there, and some other tools are also there. So today we will practice RSM in Minitab. Sorry. So in the very first step, what we will do, we will design our experiment, and after designing we will perform our experiment, which is already performed by me. I will take some example from one of the published paper. So that is already experimentation has been done. Once the experiment is done, so after designing you have to go for experimentation. Once experimentation is done, as an output of this particular experiment you will get results. that is nothing but responses of those experiments. Then you have to come back to this particular tool from with the help of which you have developed or designed your experiment, and you have to enter your responses against the design orthogonal array, whatever orthogonal array. Let us say this design of experiment is nothing but collecting the information of combination of different input variables, whatever input variables. So it is up to the decision maker or the performer who is going to perform the experiment. He has to select input variable. That selection of input variable also is a very challenging task. So many a times when you communicate your experimental results in the form of some paper journals to some reputed national or international journals, so many a time reviewer who used to review your papers, they'll ask you justification behind the selection of input variables and their range. That justification is most widely asked question. In most of the papers, I have also gone through this situation. In many of the cases, they are willing to know the justification behind the selection of these input variables, why you have selected and why only between this range. So I must tell you that this selection process is a challenging task. You have to do a rigorous work before selecting variables and their ranges. Ranges here in terms of these particular tools, Minitab, Design Expert and all, it is called as levels. And variables, we call here it as factors. That is why it is factorial. So I will take one example. I don't know the participants from which background, but since I am from mechanical background, I have done experiments in conventional machining operation, that is turning. So I will take the example of same, but it may be different from researcher to researcher or a performer to performer. Whatever in which work you are doing, there will be some factors, that is input variables. So let us say for turning, though there are number of variables are there, but we will discuss the let's say very popular variables. Those are cutting speed, feed rate and depth of cut unit also. For just for example I am telling, so it will be mm per revolution and it will be in mm. So for example, let us say for a particular operation you want to perform this particular operation. For this some factors you have to identify. Let's say 3 factors I have already identified. Some other factors are also there, like tool overhang, then tool nose radius, and so many. Environment also is an factor sometime. So here I have not considered add factor. I have kept it constant as dry cutting environment. So initially you have to identify the factors which has to be optimized. So for example, I have selected 3 particular variables, cutting variables, you can say machining variables, or more precisely, let me tell you, this can be told or this can be said as factors. So I have 3 factors. Once these factors is identified, you have to identify their labels. Okay, so most of the questions are based on these levels only. How you have selected this to this range. Let us say cutting speed, if you are wearing if it is a 3 level, so level will be low level, Am I audible, sir? Okay. Sorry, participants, for the interruption. Actually, I was like not knowing this. This is, I think, second or third Saturday, and here there is a power cut. That is why my Wi-Fi is in between turned off. Since today is no working day for us, so I am taking this session from my house itself. So I connected this through Mumbai. Sorry for the interruption. So let me resume. So I believe my screen is visible to all. Is it? Thank you. So I was discussing many of the times we face the difficulty while selecting the input variables. Less difficulty in selecting variables, but more difficulty while deciding the levels of the factors. So these levels has to be identified or has to be selected based on basically two criteria. First is the material selection. Whatever combination of material you have selected as a tool material and work material based on their properties. Let us say I took titanium grade 2 as a workpiece material, for which I need to go through some of the already published literature. What is there, because based on their inherent property, there will be some limitation of speed, feed, and depth of cut. So whatever in dry cutting environment, in whatever environment I have selected for my own experiment, I need to go through that. So this way we can identify with this tool and work combination what will be the appropriate range or levels of the selected parameters. There is one way. And second way, what we can do is, let us say workpiece and tool material we are not manufacturing before our experiment. In most of the cases, the manufacturer are different. So for tool, there are different manufacturers. The most famous and most popular is Kennametal, and then we have Vidya, and we have other manufacturers also. So whatever tool material we are procuring from the manufacturer or supplier, and at the same time, there for different workpiece material, for steel alloys there are different suppliers, for super alloys there are different suppliers, nithinol, that is nickel based alloys, there are different supplier. So what we can do is we can ask the supplier to give the complete detail along with chemical composition and along with let's say some suggested tool materials along with their levels. So they will provide you in return, definitely. But you don't, I suggest you don't blindly believe on their input. Whatever they have provided, there may be relevant, there may not be. But of course, if you are referring some of the already published research articles, don't recommend a research article published on conferences. This is my personal suggestion, because conference papers sometimes may mislead you. So always prefer some of the reputed journals. Okay, so they will definitely hint you and they will definitely guide you in selecting these levels based on the material combination. The second one is a specification of the machine tool. Whatever machine tool you are using, let us say for turning, there are a number of machine tools available these days, starting from heavy duty or light duty conventional lathe to high end or very high accuracy, high precise CNC lathe machine, and we have another advanced tools also. Okay, so we need to go through the specification of the machine tool. Okay, based on the specification and the range of, let's say their gear arrangement and all that, we can decide up to which maximum speed and minimum speed, or minimum feed, maximum feed, minimum depth of cut. So these two information you need to collect first before deciding anything and before proceeding to your experiment. So once this is done, what you can do is you can perform your experiment, you can collect the results. Okay, whatever result you want as a form of responses. One responses is measured or let's say collected, that should be recorded, and these recorded responses should be again entered to this particular orthogonal array against their input combinations. Whatever input combinations this Minitab or design expert, whatever tool has been provided you, let us say you have selected response surface methodology, so one orthogonal array will be provided to you, and against every combination you need to enter these responses, and then the next step will be analyze this one. So that analysis part also will be done by this. This is one way we can say we are not going to learn more about RSM, but on the other hand, we are going to learn more about these particular tools, application of these tools, how we can use, because the mathematical background, in the background, whatever mathematical calculations, whatever modeling or whatever thing is going on, that won't affect you and then won't disturb you by much, because you won't have to do this kind of calculation, mathematical calculation manually. Each and every calculation will be done by this particular tool, and result in the form of equation model it will provide you. Let us say for RSM, there are, let's say, most popular models are two only, that is a linear model and one is quadratic model. Out of this, quadratic is more popular, so most of the researchers and academicians, they are using quadratic model. I have also used this one, so today also we will try to focus on this, because as I told you in the beginning itself, this is a very vast topic. Covering each and every aspects of RSM within 1.5 hours will be very difficult. I'll suggest some of the reference book to you, so that it will be useful if you want to learn more on this. So today we will discuss just a single part of RSM, how we can apply as per our own convenient based on your experiments and all. So let us start today's session with RSM. I'll give a brief introduction. So this will be the discussion topic for today. So I'll be discussing introduction, then we'll see what are different RSM models are there, and what are different available designs actually. But if you talk about some of the tools, based upon different tools, there are different availability of designs are there. The tool what I am going to use today is Minitab. In Minitab, we have only second order models there, that only two, that is CCD and BBD. So our discussion will be focused on CCD only, that is central composite design. Box backend we won't see today. Okay, so one only we will decide, but actually that is not much difference. Only difference in the name of the developer, and we can say some let's say orthogonal array. As a part of opting CCD or BBD, we are going to get an orthogonal array. That is our design of experiment. So only DOE will be different if we are choosing the other one, we can say. So means you will get different combinations of alternatives to perform your experiment. That is the only one difference will be there. So we will see what are different designs available for of course first order, that is linear one, and second order, that is quadratic one. Then we will try to explain let's say I'll try to explain one of the experimental results performed by me, that is a part of case study for today. So that will be more helpful in knowing this RSM in practical way, how you can utilize it basically. And last will be the conclusion, whatever case study I will take for explanation, what the results or major conclusion I have concluded, that we'll see today. So let us start with introduction part. So introductions are very common, you can get from anywhere. So this particular method was developed by Box and Wilson. That is why he has also developed along with some other scientists Bose-Bencken in the year of 1951. Okay. So basically he was working in a chemical industry, and they were facing lot of problems in optimizing multiple conflicting parameters okay, to get best output or best responses. So to solve their problem, they have developed mathematical models. Those mathematical models are nothing but RSM only, but those mathematical models after prediction they have converted into graphs. That graphs are nothing but surface plots or surface models, and with the help of those surface plots, those graphs, they have tried to interpret the optimal result. That is why it is called as surface methodology, because with the help of this surface plot, they will interpret. As of now, whatever we have learned, let us say I discussed Mura method, so it will be completely based on mathematical calculations. So you have to calculate some values, and at the end you have to rank it. So each and everything from beginning to end, all steps depending upon some of the mathematical values. But here, what we will do, that mathematical value we will plot in the form of surface, and that surface will be interpreting to identify the optimal solution. Okay. So the purpose, of course, was same. optimize chemical reactions to obtain high yield. That let's say it was a maximization problem, we can say, wherever we want to get the maximal point, that is maximization problem. So that is, I think, known to you all, that optimization problems are categorized into 3 different categories, like minimization problem, then maximization problem. One is optimal is best, but optimal is best is very rare in actual practice. Either we have to go for minimal is best, minimum is better, or the maximum is better. Optimal values is very difficult, because getting optimal solution is quite a difficult task, whether it is a local optimal or let's say global optimal. There is a very good book written by Kalyan Mahadev. If you want to learn more on optimization, it will be very helpful to you. This is my personal suggestion. So he has written a very good book to learn constraint, unconstraint, all kind of optimization, single variable, multiple variable, all kind of variable, including some soft computing techniques also is there. You can go through if you want to learn more. So this will be a maximization problem. So that high yield, okay, with optimal setting, we can say. So this was accomplished through the use of sequential experimentation involving factors. So factors here are our inputs, okay, such as temperature, pressure, duration of reaction, and proportion of reactants. So these will be like input variables. So in terms of statistical modeling, we can say, or let us say DOE, broad sense, it will be termed as factors, and their values at different points will be termed as levels. So factors, levels, whatever DOE we will design, whatever experiment we will design, there we will find only factors. So number of factor we have to decide, that number may be 2, 3, 10, more than that also, and their levels also we have to identify, whatever, how many levels you want. So based upon the number of factors and number of levels, these tools, Minitab associated with RSM or full factorial or fractional factorial, Taguchi, whatever it may be, they will provide you a combination of factors along with their different levels. That will be our orthogonal array using which we can perform experiments. So the same methodology can be used to model, as I told you, at the end we have to model it. So modeling is nothing but developing a relationship between input and output. So let us say these factors are our input. After conducting or performing the experiment, we will get some output. So in this particular approach, at the end we have to develop a mathematical or empirical model. That mathematical model will be a function of all the input parameters. This only they have suggested, and this particular thing they have plotted in graph, that is surface plot, you can say, or response surface. Okay, the surface which represents the response, this response. So by plotting this, we will get the response surface. That is why it is named as response surface methodology. Okay, so this is some mathematical expression as I have just discussed with you. So let us say, for example, RSM is a collection of mathematical and statistical technique, as I told you, useful for the modeling and analysis of problems in which a response of interest is influenced by several variables. So response will be there, that will be your output, and definitely it will be influenced by number of variables or objectives to be optimized. So it depends whether you are dealing with a maximization problem or minimization problem. So based on this, the mathematical background or background work, I will tell you what are the principle this follows. So it will be, let's say, it is written here, no need to write here. So suppose that, for example, a chemical engineer, we have taken example from the developer, wishes to find the levels of temperature, that will be, let us say, a factor x1, and pressure, that is factor x2, that has to be provided with maximum output, that is yield. So this particular relation in the form of a mathematical model can be derived using this particular equation. So the process yield will be a function of different levels of the factors. So the particular relationship can be established using this particular equation. Y is equal to f of x1 and x2, where x1 and x2 are the factors, and there will be some, let's say, external factors. Actually, if I detail this particular factor or input variable, so factors are further divided into two categories basically. This is the second category and this is the first category, category 1 and this category 2. So first is, let's say, controllable parameter or controllable or controlled factor, and the other one is uncontrolled. So mostly noise during the experiment is considered as, in most of the cases, but it may not be applicable to you also whenever you are conducting some experiment. But of course, some uncontrolled parameter will be there, whether it is a noise or it is a dirt, it is a dust, it is a temperature, pressure, environmental condition, or whatever it may be. But obviously, it will be available in real practice. And there will be some controllable parameters, some controlled parameter. Let us say here, since it is a chemical reaction, that is why temperature is a control parameter and pressure also is a control parameter, because they have controlled, they maintained, they have the experiment, the person who is performing the experiment, he has to regulate the temperature and pressure as well. So let's say he has to set 10 degree, 20 degree and all. But for example, why I told here temperature as uncontrolled, because let us say if I am a mechanical engineer, I am doing some work, experimental work in my workshop, so definitely the environment, the experiment will be performed in an open environment. So there environmental factors like temperature, pressure, atmospheric humidity and noise, all other things will be considered as uncontrolled parameter. Whereas cutting speed, feed and depth of cut, the value which is regulated and controlled by me, I can control, I can give as an input. So those will be treated as controlled parameters. So it varies from person to person, from experiment to experiment. But in most of the cases, noise is categorized, it is, let's say, identified as uncontrolled parameter, and whatever parameter you are regulating selected as factor and different level, because it has been selected by you. So this will be categorized as controlled one. So it will be a combination. So it depends. Output always depends on controlled and uncontrolled variables and their behavior, how they behave while experimentation. That is why it is said that it will be a function of the combination of both controlled and uncontrolled variables. So it can be depicted as this particular equation, but we did not to worry about this. Those tools like Minitab and Design Expert, they will help you to directly reach to the mathematical model. This equation you need not to develop by your own. This software will provide you, this tool will provide you. Just for understanding, we are discussing. So here, this epsilon represent noise or error. Okay, it may be noise error, but you can say this is uncontrolled variable basically. Okay, observed in responses. Then if we denote this particular thing using some denotation is there, reta. So this particular term can be termed as a surface, as I have already told you. And this surface, since it is dependent on this particular y value, that is response, so that is why it is named as response surface. And this only we have to plot it. How we can plot? Let me tell you. So for that particular example, whatever we have selected, this is the response plot or response surface. So in this particular method, this plays an important role. I will tell you while discussing the example how we can plot response surface. So you can see here one axis will be, and of course I forgot to tell you, it is a 3D surface plot. So all three axes will be there. So in two axes our two variables are there, that factors are there, okay, along with their levels. So these are their levels basically, okay, 100, 120, 140, 160 and on. And pressure we have taken from, let's say, 10, 20, 30, 40, whatever the unit is, it is immaterial. And based upon this particular combination, the RSM will provide you orthogonal array. Once orthogonal, using this orthogonal array, you have performed the experiment. After experimentation, you have measured the yield, and that yield is now plotted here in the form of surface. So plotting this surface manually is quite difficult. Okay, very difficult, I must say. But we are fortunate enough. We are having let's say sufficient tools, useful tools, we can say. If we are putting input combination along with output, you can plot it. Obviously, you can plot this one using some other software tools also, like graphical representation tool like Origin, or other tools are also there. You can explore more, but RSM will also give you this kind of response surface, and you have to interpret. So here, since it is a maximization problem, you have to identify by observing this plot. Yes, this will be the maximum value of yield, and you have to, let us say, interpret that here the optimal solution will exist. So you can extend this one towards both the axes, x-axis, y-axis, whatever it may be. You can join these two lines in both the axes, and you can identify what will be the value of response in a combination of x and y. That will be your optimal solution for this particular problem. See, so this will be optimal solution, and at the same time, while interpreting your result, since you might have gone through several papers, it is not only result, it is result and discussion. You have to discuss in detail also. So whatever let's say trend you are observing here, the trend of the response surface, that has to be explained. So let us say from this point to this point, you can say that the temperature is increasing in nature, and from here to here also this pressure particularly is increasing. Okay, so that behavior of this response surface you can interpret by behavior of the plot by visualizing this one. So this is your response, that is also in increasing manner. So you can say once we are increasing the temperature from, let us say, 100 to 120 up to approximately this point.
ये हमारा क्या होता है, इनवर्स होता है। तो स्टूडेंट हम जानते हैं यहाँ पे इनवर्स ये किस होता है कि ये क्यों में जाए, तो यहाँ पे इनवर्स एग्जिस्ट कर रहा है, आइडेंटिटी एलिमेंट भी यहाँ पे होता है हमारे पास, यहाँ पे
somebody else is speaking, I think.
और यहाँ पे क्या है, रेशियो नंबर -1 को छोड़, राइट। तो इस तरीके से क्वेश्चन यहाँ पे सॉल्व कर। नेक्स्ट क्वेश्चन है स्टूडेंट, एग्जांपल नंबर 3, कहां से डिफाइन a star b is equal to b plus 1, show that the thread star is an abelian group. Student,
Hello. Okay, there was some interruption. Now is it okay? Okay, so what we can say is we observed an incremental behavior on response, that is from temperature 100 to 120. By increasing the temperature further from 120 to beyond, let's say 40 or 160, that yield was decreasing. So up to this point it was increasing, up to this point it was decreasing. At the same time, you have also to explain why it is so. So based upon the experiment and literature and theoretical background available with you, you can interpret that one. The reason behind the trend of the response surface, that also has to be explained. So since this is the example from some others work, I don't know what was the reason, but of course we can interpret in one way the trend of the response surface. So likewise, you can also explain the trend of the yield with respect to pressure. So that will be the explanation which should be included or interpreted by seeing this particular response surface. So this is how you can obtain your optimal solution. Their trend also, and you can explain. So a three-dimensional response surface showing that expected yield, whatever is the maximum is possible, maximization problem with respect to temperature and pressure. We will also try to plot a response surface. I will tell you how we can plot using Minitab. Next, if you project these surfaces on the bottom surface here, this is called as contour plot. So in the next slide it is there. This is the explanation of the previous one. Let me skip this one. Next will be contour plot. Okay, so contour plots are nothing but a circular representation of the surface plot having details of variation of the output with respect to the selected input variables. So you can interpret here also. You can see this center point is the maximum point. So this is just nothing but the projection. Whatever maximum point I have told you in the previous slide, that maximum yield, since it was a maximization problem, so this will be projected here and which will call as maximum point. If you trace in both the direction, you will get your optimal combination of temperature and pressure. So at this temperature and this pressure, your yield will be maximum. This is how you can interpret your contour plot in addition to surface plot. This is another way of representation. There is no difference at all. In principle, in surface plot and contour plot, there is only one way. This is the projection in 2D and this is representation in 3-dimensional, and in both, using both the plot, you can interpret your result. But of course, these contour plots are more precise in nature, because now once it is projected on this particular surface, it will give you the exact value or exact point where the maximum or the minimum. If it is minimum, then surface will be like this. Minimum point lies or minimum response lies along with the combination of input variables. So you can interpret in such a way. So this is how basically we do while solving our problem or while optimizing our problems using response surface methodology. This is the main two things we can say. In addition to that, we will also form ANOVA table, that is analysis of variance. I will share in upcoming slides. So this is the publication statistics in comparison to MOOMESA. You might have observed, I have checked like past 5 or 6 years. So the number of publications were in 1,000. The maximum in present year was, let's say, 3,000 something. But as I told you in the beginning itself, this is very popular method and very useful, most widely used, you can say, among all existing optimization techniques. So you can see, though there is not let's say similar or increasing or decreasing trend in the past decade, which is going to end by this year 2020. So in this particular decade, the entire 10 year, you can see the number of publications are more than lakh. Only this year it is less only. So again, this I have taken from Google Scholar when I was preparing this PPT. So you can see the popularity of this particular method. So like more than 1 lakh, more than 2 lakh papers are publishing in a year application or applying RSM method in wide area on wide let's say in domains. So it is like independent of domains, you can say. It is, I cannot say that it is only restricted to mechanical experiments. Wherever you are doing some experiments, wherever you are dealing with some issues while minimizing or maximizing the responses, you can use this particular method or tool. Obviously, before the experimentation, you have to first design your experiment using that particular tool only, because that design has to be adopted from this tool only. Then only you can perform and analyze the results using RSM. Okay, so types of RSM, there are basically 2 types: first order, second order. First order is almost saturated, nobody is using these days, very less users are there. Of course, because most of the problems are critical in nature. You might be observing whenever you are doing some experiment, there are a number of variables to be optimized, precisely to be minimized or to be maximized, or conflicting in natures also. At the same problem, you may be having some factors or variables which has to be minimized and some variables which has to be let's say maximized. So in conflicting in nature, so first orders are, let's say, not that much adequate to provide you the best optimal solution in comparison to second order. But second order, what is the advantage of second order? Second order directly did not give you the answer or the model from only belongs to quadratic models of second order. What it does is, it also tries to solve the problem initially using some linear model, and if it feels that this linear model is not sufficient, then it includes some of the terminologies of quadratic model. So you can say this is a second. That is why these approaches are more appropriate and more efficient, you can say, more effective in reaching towards the optimal solution. So we will just see what is first order model. So as I told you, it will be linear in nature. So first order is nothing but linear only. Second order is quadratic along with this error. So you can see here, if you see, so this will be some coefficient. This will be our linear, that is first order, and it also have quadratic, and these are called as interactive. So you can see these are individual or linear parameter. So it is a combination of all linear parameter, quadratic parameter. Let us say one factor is x. So quadratic will be x cross x. Second is y, then y cross y. So x is square, y is square, and x and y are independent. So interaction between x and y, x cross y, that also will be explained and derived. So that is called as interaction. So I believe these particular terms are very much clear to you, because you, as per the schedule, you already have gone through basics of Tabuchi and design of experiments. So you might be knowing linear, quadratic, and interaction. So second order offers you all terms, including linear, quadratic, interaction. So you can do the analysis in more effective way, since it is inclusive of all kind of possible parameters. How we will perform, we will see. Okay, so this is the, let's say, background, mathematical background, which is followed by RSM, but no need to worry. Okay, because tools are there which will help you, but just for your knowledge I planned. So you actually RSM, as I told you, it doesn't provide you directly second order, doesn't take you. So it is let's say nothing but a sequential procedure, basically commercial one. It is a sequential procedure. So it first tries to solve the problem using some linear model. If it is not possible, it will go to the quadratic, then interactive. So all kind of experiments inside it will do. And the method and the approach, mathematical approach used by this particular method or tool is steepest ascending or steepest descending method. So these two methods, if you want to learn more, that particular book, whatever I have suggested, that is Kalyan Mahdev, in that particular book, it is given in detail. You can explore it. So if your problem is, let's say, maximization problem, you are here and you want to reach here, this particular method will help you to reach from here to here in a sequential manner, and you will feel that it is a process of climbing a hill. If it is a minimization type of problem, if we are here and you want to reach here to the minimal solution, it will be like descending into a valley. So that is why it can be called as a sequential. That is why this process and this particular method is that much effective, because it follows a sequential procedure. So point to point it will travel. If you learn this particular method, these two methods, that method of steeped ascent for maximization problem and method of steeped descent for minimization problem, you will come to know. But we are fortunate enough to have Minitab and Design Expert kind of tools that we need not to worry about this entire procedure. But for the knowledge, for the sake of knowledge, I just included these two slides. So step to step, it will travel and it will reach to the optimal solution, basically. Okay, and designs for first order and second order. So there are a number of designs available for first order as well as second order. Okay, but we will be discussing only one particular thing, that CCD1, because all designs if we will discuss, it will take 1 week, more than that even, I don't know. And I don't know all the methods also, since I have used this one only, I can tell you. But of course, there are a number of similarities, there is no issue. But let's say, don't worry, this will be the very popular one. You can explore whatever research area you want and you are working. You can see 90% or more than 90% of research works are based on CCD only. So that is not a problem. With this particular model, you can do your own work. You can solve your optimization problem. So in the first category, first order designs. So this design you have already studied in simple DOE, that is 2 to the power k factorial, full factorial, fractional factorial, you have seen already. Then we have Packlet-Berman, then simplex design. This is not a part of mini tab design expert. I have not seen. If it is there, then I need to check. But not very few people are using this 3. But of course, in second order, this is not being used most popularly, most widely. But 2 and 3 is being used, out of which the central composite design are used mostly. So I will discuss today this one, not to Volkswagen or 3 to the power k factorial. Okay, so we will discuss this one particularly, and we will try to learn some of the operations using Minitab also. So this is some of the details about CCD. So CCD actually is a combination, we can say, of a previous one also. So a complete factorial design. So factorial, that means factors. Okay, so factorial points are nothing but corner points in case of CCD. I will tell you with the help of a graphical representation. Then in addition to corner point, it also has some axial point that is called as alpha here. Okay, so axial point consisting of 2k points arranged so that that distance from alpha. Then we have last center points. So how corner point, axial point and center point can be represented, that can be understood from here. So this is called as central point. This is called as corner points. Okay, this is just let's say arrangement, and this is called an axial point in a CCD. So CCD have 3 different components: central component, then corner component and axial component. Numbers depends, because in CCD also there are 3 different provisions: no blocks and with blocks. In with blocks also, what how many number of blocks you want, that depends actually. Okay, so it consists of 3 particular elements: 2 to the power k, then 2k, and this one. This is the central one, and this is the axial one, and this is the corner one. Okay, so if you select the value of k is equal to 2, what will happen? You will get total 4, and this k also will become 4. So 4, 4, 8 plus here. Usually it is equal to k, n naught is equal to k, and the distance alpha. So that alpha value also you need not to calculate manually. It will be provided in the software itself, the tool itself. But usually it is a alpha value is most widely taken as root of k value. Whatever k you are taking, k is nothing but number of factors. Whatever factors you are selecting, it is a 2 factor, 3 factor, 4 factor. So RSM always starts with minimum number of factors as 2. So let us say if you have a 2 factors, then how this can be represented? So 2 to the power 2, it will be 4. Then here again it will become 4. And this is, there is no fixed value for this, but most widely in most of the cases it is taken as equal to k. As I told you, alpha is equal to root of square root of k, and this n naught central points is considered as equal to k in most of the cases. But if in your particular problem you can vary also. So if you see, the total 10 combination will come. So you can see 10 combinations as per RSM is given here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all these 10 points how can be located in a CCD design. So this is how it happens, but it will be happening in the background. You will not come to know that how it is happening. You will get only responses. Just wanted to explain that how it can be represented mathematically. Okay, so this is the some of the details given there. Whatever center point I have told. Okay, there is not much thing here to discuss. So now let us come to the main point. So this is all about theoretical part. Okay, so now we will try to understand how we can solve our problem using RSM method. So there are first step, as I have told you, the design of experiment. So designing of experiment can be done in 2 ways. First, directly from RSM, that Minitab, you enter your values, it will provide you this. Or what you can do is, you can refer some of the already published work those who have already adopted. So that adopted design you can also adopt for your work if you feel convenient. But of course, the condition will be you need to set the value of factors and their levels as per your convenient and availability. But so DOE again, that is why it is more flexible basically. It will give you coded value also, uncoded value also. Uncoded value means the factors and level with exact value, whatever you are selecting for your experiment. Coded means what you will do, this RSM, it will ask you what will be the minimum value, what will be the maximum value, and minimum value it will consider, let us say +1, and maximum minimum it should be -1 and +1, and it will generate one DOE and it will provide you one orthogonal array. So this is one way, or otherwise you can adopt from the already published. This is one of the published paper from which I have taken. So what I have done is I have adopted the design of experiment from some of the published paper. That is almost easy task, not that much difficult. Yes. Okay. Maybe some issue. So what I will do is I will leave the meeting and again I will join them. Okay. Is it visible now? Okay, thank you. Actually, let's screen share was stopped. So we will take one example. So this was the experimental detail, whatever I have conducted experiment. So I took cutting speed, feed rate, and depth of cut. Values. So what you can do is once it is decided, once the domain of your experiment is decided, what you can do is this domain can be entered into Minitab in RSM platform so that it will provide you this particular orthogonal array. This is the coded value about which I was talking about. This is uncoded and converted, you can say. So let us say +1 indicates the highest value. So you can see wherever +1 is written, I have written 87. Wherever +1 is written, I have written 87. That is the highest value. And wherever level 2, that is 0 is written, so in place of 0, I kept 67. So like this you can do. So this coded value, actually I have taken from some of the published paper. But this coded value can also be generated in RSM. Now let me show you how we can generate this coded value. So for this, we will go here. This is Minitab version 16. It is visible to all. My
Yes,
screen
sir.
is visible, na?
Yes, sir.
Okay. So here we have to go in. So to learn this particular software, one dedicated book is there. I will suggest you. I think I have somewhere I have written by Douglas C. Montgomery, Design and Analysis of Experiments. So this book is explained each and every point. Let's say from file menu to edit menu, data, and whatever sub points are there. Each and every point is described in very precise and very let's say explanatory way. You can refer that book to learn more. Since we are going to learn only one thing, that is come under statics, under DOE, that is design of experiment, and you might have already covered this one, factorial. Today we will be seeing that is response surface methodology. So you can see it is under this particular thing, statics, then DOE, then response surface. So here you can see create response surface design. Once
Sir,
you create this one,
excuse me, sir, we can see only your PPT, sir, not RSM design matrix, only the table is visible.
Okay. Actually, I have opened in my screen this mini tab also, but you are not
No,
able
that
to
is,
see.
we cannot see the mini tab. We can see only the matrix PPT matrix design, RSM design matrix table 2.
Okay, madam. Okay. Thank you. So what I will do is, let me close this one first. And I will again open. Now, is my screen is visible? Can you see my desktop?
No, sir, same. I think myself, I can see only the table. I mean, the earlier slide only.
Okay, madam. Actually, there is network issue. I think since I am operating using my mobile, there may be some problem. Due to power cut, actually, Saturday there is a power cut here in Karnool. So my Wi-Fi is turned off now. Okay. So now can you see my desktop?
Yes, sir. Yes, sir. We can see your desktop.
Okay. So now I am opening mini tab.
Yes.
So it will appear like this.
Yes.
I believe you all have a mini tab with you.
Yes, sir. We can see this and we have, yeah.
Yes. So here stat option is there. Under stat, you can see DOE, and under DOE, this factorial is already, I think, discussed. We are going to discuss response surface methodology. So under this, create response design will be there. So once you click here, this dialog box will open. So here you can see there are two different types of second order response surface or RSM models. Whatever I had discussed now, that is CCD and BBD. So I will take example of CCD. As I told you, the minimum number of factors permissible in CCD is 2 and the maximum permissible factors are 10. If you are having more than 10 variables, then it will be difficult to solve that optimization problem using RSM. Similarly, if your number of factors is varying from 3 to 10, but except 8, you can see here 8 is missing. Okay, so for 8 number of factors, it is not recommended. So we will see as let's say this one particular for 2 variables. Okay, so number of factors you can select here. It is starting from 2. You can see there is no one option, and since CCD is selected from 2 to 10, all numbers are mentioned here. So you can select any number of factors as per your experimental let's say selection of variables or factors, and you can just see the design, available designs it will show you. So here in horizontal axis you can see factors varying from 2 to 10. So since we have selected 2 factor, so in this particular category there are 2 orthogonal array available. So it is showing only 2 orthogonal or CCD available here. You can see in this particular category, one is unblocked category, the other one is blocked category. So unblocked means there won't be any block. Block is cubical form. So if there is no block, it will your experiment will complete within 13 experimental trials or experimental runs. If you are opting any blocks, it will be providing you total 14 number of trials or experiments. Only number is changes. Other than this, you will see the difference in the combination of the factors. So these two differences will be there. So let us say by default it is selected as 30. Let me click as OK. Then you can see the designs. So designs also, as I told you, with that is both are full design. One is of run with total runs 30 and one is with total runs 14. So there is no need to worry about this. Total values and everything it will tell you. There is no issue at all. So total this number of points are there. Alpha value also it is already collected. Calculated. Let's say we have selected 2 factors. The k value is 2. So root of 2 you can see. As I told you, alpha in most of the cases is taken as root over k. So it is 1.414. So that is immaterial basically. Just for knowledge I am telling. So this will be selected. Once you click OK, there is not much thing in here to check. Then factors. You can see the factors. So this will be coded value. You can edit these things as per your convenience. If your factor name, cutting speed, you can write here. You can type here. if you know, you can type anything, it will come. If you are typing, if you are not typing, there is no issue at all. So A, B, they are low and high, means minimum and maximum. Though you have selected 3 levels, in RSM you have to enter only minimum and maximum. Intermediate value it will automatically take with the help of the tool. It will calculate. Okay. In factors, this is the option. If you see the options, there is not much thing. No need to see anything. And here in printed results, yes, by default whatever is selected is okay. Summary table. Once you click OK, it will provide you this particular thing. So you can see total number of runs are 13. And here this combination is given. What will be the value of A and B? This is called an orthogonal array. Okay. So total run order you can see from 1 to 13. Total 13 experimental run having combination of both the variables A and B. So what does it mean is the first experiment you have to perform using A value this much and B value this much. Since it is a coded value, uncoded value can be replaced here in place of coded value if you are taking help of Minitab. Okay, so that is one way. The other way, coded value you can adopt from any published work and you just convert as per your uncoded value and you will get that particular table and directly perform the experiment and type your responses here. So what I have done in the next stage is, in the next table, if you see, so this was taken from some paper and I have get this uncoded values. So based upon this orthogonal array, I have performed the experiment and I got these results. Let us see. So total 6-7 parameters responses I have measured and estimated, but since the time is very much limited here, I have included only 4 and that too I believe 1 or 2 I will discuss. Okay, because time is already crossing, it is 11:26 because of internet and some interruption. So let me at least explain one how we can do it. So we will go directly. So this will give you the response table including the combination of all the experimental runs. So this is L20 setup actually I took for 3 factors and 3 levels. So once you have selected 3 factors, 3 level, it will give you either L16 or L20. So I adopted L20 orthogonal array, performed the experiments and recorded the results. The recorded results are presented here in this experimental results table. So you will get after the experimentation this table. Now for analysis again you have to go to RSM, that particular thing. Okay, so let me take you there again. This one. So for this, let me first open that table. That is experimental results. So this is the experimental result table. So what the other way you can do is all 3 input and any output, whatever output you want to analyze first, you can copy here and you can open your Minitab. So let me close this one and I will open once again a fresh screen. So if you have adapted, so what you can do is directly, since we have adapted from somewhere, directly we can paste here. Is it visible now?
Yes, sir, it's visible.
Okay. So this is our C1, C2, C3, the combination of input variables, and by performing our experiment, turning experiment at a speed of 87.0.14 and this one, that feed force value, whatever we have received in newtons, are 162 point this. And similarly, we have repeated 20 times whatever as per the orthogonal layout we have received from RSM. Now we will analyze. So we will go to the same heading, that is statics, then DOE, then response surface. Now once input and output will be entered, another points, all other options will be enabled. Earlier you might have observed only create response was enabled, but now analyze part also is enabled. So you can click here, analyze response surface. Once you click here, since this is already adopted from some other papers, that is why it is asking permission, because this particular set of design is not designed here. If you might have designed here, then directly it will go to the this particular section, you enter your mark. But since it is not designed here, I have copied from somewhere else, that is why it is asking the information about input and output. So you have to click yes here. Factors, because it has to understand what are the factors you have taken. So out of these 4 columns, column number 1, column number 2 and column number 3 represents the factors. I need to select all 3 by clicking here, double click, one double click. So one factor is cutting speed, another factor is feed rate. Just you have to double click here and it will take. Okay, so that factor has been selected, and you have to identify low and high values also. So it will automatically take, but if there is any correction, you can check. Okay, so for cutting speed, lowest value is 51 and maximum highest value is 87, whatever I had decided. Feed depth of cut, it is correct only. In most of the cases, it will get correct. These are uncoded values. Then designs. So in designs, nothing is required, I think. You just click OK. Then now it will ask you what is the response. So the left out column, that is feed force, is our response. Double click here, it will come here. Okay. Next, different options are there. Let us go one by one. First, you click on terms. So in older version of Minitab, all available terms will be displayed here. Whatever term you want to add during modeling, you can include this side. Since this is the I think newer version, not latest, I can say this is version 16 only. So in version 16, all variables by default will be selected. So you can see right side selected terms. But if you want to exclude any term, so see A, B, C, they are linear term, independent variables. A square, that is quadratic term. B square, C square. Then A cross B, A cross C, B cross C, that is interactive term. So as I told you in the beginning, quadratic model will provide you all the possible combinations: linear combination, quadratic combination, interaction combination. And here also you can see the model is selected as quadratic. You can select some different model as well, but quadratic is always preferred. But if you want to exclude some of the terminologies, some of the term from your model, from here, you can exclude, no problem. You can select here and you can click, you go this side, this arrow key, it will go. Okay, that is not a problem. By default, in this version, all is selected, but you can deselect as per your convenient, as per your own requirement. If you want to analyze only linear terms A, B and C, you can analyze. If you want to analyze only quadratic, you can analyze. If you want to analyze only interactive, you can analyze only interactive term. It is up to you. But in most of the cases, if you refer some papers, they are analyzing all 3 types of the parameters. So here simply we need to click OK. So it is all about terms. Then prediction. So in prediction, whatever predictions I have told you, it is a predictive model also, which establishes a relationship between response and input variables. So response should be equal to a function of all 3 parameters. So here all 3 factors you need to select. There is a hint also, factors only you have to select. So let us, by double clicking, you can enter all these 3: cutting speed, feed rate and depth of cut. Okay. Level of confidence, by default it is set as 95. I think it has also been discussed while discussing DOE. So in most of the statistical approaches, we prefer only 95% confidence level, which means the probability of acceptance value, that is P value, should be equal to or less than 0.05. Then only our model will be effective at 95% confidence level. So this is already selected, no issue at all. Let us click OK. Then next is graph. So whatever graph you want to interpret in your result, you can click. So there are 3 different options: regular, standardized and deleted. In most of the cases, I refer standardized one. The value should be standardized. Graphical representation also, there are 4 different types of graphs are there, but I used to prefer only this one, normal plots. But you can take all 4 in one or all 4 independent by clicking each and every plot. It is up to you basically. Okay. And how to interpret the graphs, you can refer many papers. Plenty of papers are there which will help you to understand how we can interpret the graph. Okay. Then the next is results. So by default, whatever is ticked, it is clear. Whatever unusual observations are there, that also will be recorded in addition to the table. So in addition to above, basically. So above ANOVA table is the let's say most important thing to be included. So ANOVA table, obviously we will take, click OK here, and next, since everything is checked now, let us click OK. Once you click OK, this is the graph which we have selected, normal plot, that residual points. We will discuss later this one. Let us just check this particular graph. So here the most important thing we have to observe is, so this is not estimated, not regression, analysis of variance we have to see. ANOVA for feed force. So since space is less here, some up to adjacent MS it is given, and F value, P value is written needed, bottom 0, 0, 0, 0, this value. Let me show you this in a single particular graph here. I think yes. So same value was observed here. So you can see this particular slide. It consists of linear. So since time is already exceeding, I will complete by discussing this one only. Remaining is same only. So this is linear, square, interaction term. So linear, independent, square, quadratic, and interactive. Okay. So there is not much thing in detailing here. Only you need to take care of this P value whenever you are plotting ANOVA, that is analysis of variance. It indicates the significance of each and every factor, independent factor, quadratic factors, and interactive factors. So as we have set the confidence level as 95%, which indicates that the probability of acceptance, that is P value, should be equal to or less than 0.05, because 95% confidence level is there. So you can see almost all the values are less than this particular value. Means we can conclude by observing this particular ANOVA table that all three types of terms, linear terms, quadratic terms, and interactive terms, are significant to minimize the feed force. Feed force is minimal is better criteria. Force always we want to minimize, since it is a minimization problem. So to minimize this one, all parameters are significant. Then this table also helps us to identify among all the parameters which independent or which quadratic or which interactive parameter is the most effective. So that can be said by going through this P value. Okay, the least P value, but the cases as this, all P values are almost equal. So it is very difficult to say that which independent or which quadratic interaction or which quadratic parameter is most effective one, most influencing on minimizing the feed force. So there is one more way. This won't be provided by Minitab. This you have to calculate manually. Percentage contribution of each and every parameter. You can see all independent parameter, quadratic parameter, interactive parameter, percentage contribution. This can be calculated by dividing sum of squares divided by total sum of square with respect to each. So let us say we want to calculate the percentage contribution of A. So the value of sum of square, that is 6308.7, divided by total sum of square. If you have calculator, you can just cross check. I don't know, because this paper I had to publish 2 years back. It will provide you this value. Okay, so what you can do is, in the next step, you can calculate percentage contribution. You can refer the paper which I have cited for this one. I have mentioned the formula to calculate percentage contribution also. So by calculating this value, now it is very much clear which individual parameter or quadratic parameter or interactive parameter is most influencing in minimizing the feed force, that is response. So since this is the most influencing parameter, this is the highest value, I must say, or I can conclude from this ANOVA table that cutting speed, A is nothing but cutting speed, is the most influencing input variable which helps in minimizing the feed force during the selected range of machining parameter. Whatever we have selected in this range only, to minimize the feed force, this cutting force is most effective one. Followed by interactive turn B and C, followed by this. This much explanation is more than sufficient. Okay, this is how we can interpret ANOVA table, and this is the equation. Whatever we will get in Minitab, if I will on this one, it is there actually. So in addition to ANOVA, it will also give you quadratic equation which represents the relationship between output, that is feed force, and coefficients including all the parameters. So these are independent parameters and these are quadratic variable parameters and interactive, since we have selected all. So in the form of all, it will provide you. Simply you can type this equation in any Excel sheet and you will get the predicted value. So this is the predicted equation which can predict the relationship between y and x, that is input and output. So this equation also provided by RSM. Once the equation is established, you can estimate the predicted value. So predicted value and experimental is already measured by you. That value is calculated using some Excel sheet. You can plot a comparison graph. So you can see how your model is capable in predicting, how close your model is capable in predicting the experimental values. So this is graphical representation, and after that you can calculate. If you do some error analysis, so you can calculate the error also, predicted minus experimental, okay, into 100. So you can see the estimation or percentage error, how it is deviating. So this is underestimation. So underestimation doesn't play any role, but if it is overestimation, then it will be a matter of worrying. But you can see in maximum side, plus side, the maximum error is, I think, within 5%. Means what we can conclude from here is our suggested model, whatever model we are suggesting, that model which represents the relationship between output and inputs is at least is within the acceptable range of error. Means the percentage error, the maximum error is almost less than 5 or almost 5%. That we can conclude. So similar observation has been done for radial force. I am not discussing. I have already crossed the time. Same thing is there. If you understand the first thing, error graph. This is for tangential force, error graph, comparison graph and error graph. So this is how we can conclude. So the conclusion part I have included here so that you can understand. I have told you that percentage contribution of cutting force was noted as this much, 48% or around 49%. Okay, for feed force, and this much for Fy, this much. So in most of the cases, it was the maximum influencing parameter that can be concluded. So here also it is written. The results of ANOVA tests revealed that almost all the performance measures reported in this study were primarily influenced by cutting speed. So you can see here, and whatever error we have calculated, so we can say that whatever quadratic model we have developed using RSM, all model were under the error of 6%, within 6% approximately. So this can be said as very good predictive model. Okay, and this value, R square value, I think you might have discussed, coefficient of determinant. It is always preferred as high as possible. Minimum value if 80 or 82%, that is also okay. But we received more than 95% of R square value. That also shows that quadratic model is adequate. Okay, so these are the reference. This is the first paper from where I have taken all the data. This is all about today. Sorry for the delay, and thank you for bearing me such a long time. If you have any doubt or clarification, please let me know. I will be happy to answer your doubts. Am I audible? Am I audible?
sir. Yes, sir.
I am done, ma'am. From my side, I am done. If there is any doubt from participants, I will be happy to answer. If there is any, otherwise, we can conclude the session. So I think there is no doubt.
Okay, sir. I think there is no query because
Okay,
you
sir.
have printed your lecture very efficiently, and I hope
Thank
that
you, sir.
all the participants have understood your lecture. And on behalf of our institution, we are very much thankful to you for giving your expert lecture on RSM, and I hope that all the participants have understood your lecture very well. And again, I am very thankful to you on behalf of all the participants and from the institute. Thank you, sir.
Thank you, sir.
for your
Thank you very
expert
much
talk
for
today.
giving me this opportunity. So I thank the organizing team of Shankaracharya Technical Group and for giving me this opportunity. I thank all the participants for bearing me for 2 long sessions. Thank you very much. If I have committed some mistakes, please forgive me. And please feel free to ask any query in future also. If you want to ask related to any MCDM criteria or optimization technique, I'll be happy to sharing my let's say views on that to you guys. Thank you all of you. Thank you very much.
Sir, there is a question by Ashutosh Tiwari. What is the interpretation of the Pareto front graph when using 3 objectives?
That is not a part of actually this RSM. RSM we plot only 2 kind of plots: response plot, response surface, and contour plots. That I missed actually because of the time limitation. But interpretation, how to interpret, I had explained in the beginning. But how to draw in Minitab, that is left actually. So that is very easy. In that Minitab itself, there is a title called graph. So if you select that graph, in the bottom response surface is mentioned there, 3D response, and as well as contour plot is also. You need to select any one, and you have to select all the axis values, x value, y axis, and z axis. It will give you that particular graph, and you can interpret that Pareto. This graph representation, I don't know. It is a part of RSM. That actually I don't know, but RSM includes response surface and contour plots.
Okay, sir. Thank you for your answer and for clearing the doubt of Mr. Ashutosh Tiwari. Anybody else? I think, sir, there is no question. So again, I am very thankful to you.
Thank you, sir. Thank you very much. Shall I disconnect?
Yes.
Okay. Thank you, sir. I'm disconnecting now.
Hello. Hello, can you hear me? Hello, can you hear me?
Yes, sir. Yes, sir.
Okay, now I'm sharing. I think the time is already over, correct? So I should start now. Am I right? Shall we start?
Yes, sir. Yes, sir.
Okay, fine. So, good morning, everyone.
Good morning to all. Good morning to everyone. Thank you for joining us for today's training program. My name is Gurmeet Singh and I am Assistant Professor in Mechanical Engineering Department at Sri Shankaracharya Technical Campus. Today we are all gathered here for becoming part of day 6 of 1 week AICT sponsored online short-term training program on multi-objective optimization methods for engineering and scientific applications. Organized by Department of Mechanical Engineering, Sri Shankaracharya Technical Campus, Sri Shankaracharya Group of Institutions, and sponsored by All India Council of Technical Education, New Delhi. Today's eminent speaker is Dr. Asharjee, and let me introduce Dr. Asharjee. His profile. He is assistant professor at BITS Pilani Hyderabad campus, and he completed his education from BTech in Mechanical Engineering from Bundelkhand Institute of Engineering and Technology, Jhansi, UP. And further, he pursued his PG in Mechanical Engineering, that is Masters of Engineering in Mechanical Engineering from BITS Pilani campus in 2008. And he completed his PhD in Mechanical Engineering in the field of Topology Optimization from BITS Pilani campus. So, area of specialization, his area of specialization is optimization, and his work experience, if we talk, he's having very vast work experience into teaching field since 2008 and has served in more than 4 reputed institutes. He has got more than 45 publications and contributed in renowned journals and conferences. He has also got sanctioned 6 sponsored projects as PI and co-PI from various central agencies and organizations. Now, just a little housekeeping before we get started. If you have any questions during presentation, please type them into the question box and in your chat box control panel. I will bring them up during the presentation, and we also have time for questions at the end. Now, without further ado, we will turn the time over Dr. Asharjee. Sir, please.
Yeah, I think you can hear me and you can see the slides also, correct? So, I hope this is the last session, isn't it? This is the last session or technical session of this training program.
Yes.
And I'm fortunate and thankful for the organizers to provide me the opportunity to start the session and to complete also this session. So I have taken the first session also, and I'm fortunate to take the last session. So in the first session, we have seen the basic of statistics, and now in the last session, we are going to see the application of optimization in mechanical design or mechanical engineering design. This area is also very vast, and let us discuss many frontier area into this one. Optimization was used in design, you can say, from long back, centuries back, and you can say in ages also. People used to do the optimization. Now, in mechanical design, what is the role of optimization? And first of all, we have to understand why optimization is required in the mechanical design or any kind of design. So actually what happens, people use this term optimization very frequently, but actually we should use this term where a particular application is found. There is a condition for optimization. There is a condition for optimization. What is that optimization condition? what is the condition for optimization? So we used to have a parameter. Parameter means specifically input parameter, and we design something which gives output. Okay, so this is also a parameter. So between these two parameters, we can see a particular relation. Sometime, if it is a positive relation, and then you can see that the output here, you can plot in y-axis, and in x-axis we can plot input. So as the input increases, output also increases. Something like this. This may be a positive relationship. Both are increasing. Okay. So this is one type of relation with one parameter. Now if you involve multi-parameter here, multi-parameter, then what happens? So this is, let us say, parameter number 1, and there is another parameter P2, let us say. So you can say it reduces like this. Okay, P2. So you can see that there are two parameters, and with respect to each parameter, P1 and P2, the function increases or decreases also. So you can take it in other way. Let us say that it decreases in other way. So it will take the form of this increases and it decreases. So let us say it is like this, and this is P2, similar one, not much difference. So where is the optimum point? How can be optimized? So you can find that you can keep on increasing this one, and it reaches to the maximum value of parameter here. So this is the output, maximum output we can obtain from here. In other condition it is higher, but the parameter level is also not correct. So if you go for very high value of P1 and P2, it will not give you the optimized value. It will come somewhere in between or lesser than this one. So at this condition, you can see that the shaded area is the region of optimization, wherein we can operate the equipment and find out the maximum output. So optimization is applied. We were talking about condition for optimization. Optimization is applied when we find out some negative relation of or opposite relation of the parameter with respect to the output. For P1, you can see P1, the output is proportional to P1, and here you can see as P1 increases, the output is inversely proportional to P2, 1 by P2. And we have to operate in both parameters, so there must be a point at which we find out the maximum value. And there may be a constraint that P1 plus P2 is equal to a number A, let us say. So if you increase P1, obviously P2 will be equal to A minus P1. So it means these are not independent. If you increase P1, P2 is going to be decreased. So that is why we need to have a particular value. For example, let us take an example of cylinder height and diameter. This is a normal conventional problem which we use in mathematics in maxima and minima. So this is the diameter and this is the height. Material volume is going to be fixed. Volume is going to be fixed. So it means D and H can be related together. D and H is related together with respect to volume. So we can increase the volume, we can decrease the volume, we can increase the surface area or decrease the surface area. If you wanted to increase or decrease surface area or related to some properties, we have to get an optimum value of D and H so that the required function can be maximized or minimized. So optimization is not only if you get an equation in which you can always increase the trend, it means that there is no scope of optimization. Let us say this is P1 and this is the output and this is P1 value here. So it means if you keep on increasing P1, you get more output. There is no optimization here. You have to operate a highest value of P1. Similarly, if it is P2 also, it means you have to keep on increasing P1 and P2. Or if there is a condition in which there is no relation between P1 and P2, it means there is no constraint here. So it means you can go with the highest value of P1 and lowest value of P2 and you get the highest value of the optimization. But if both are dependent on each other and bounded together, it means we can use we have to use this P1 and P2 in such a way so that you get the maximum output. And this is what we call it as optimization. So optimization is required when we come across such situation where the inputs are limited and inputs are dependent on each other, and based on these input we can get some output which has to be maximized or minimized. So that is what we got optimization in engineering problem. And for example, this is the example of optimized dimension where the volume is or the surface area is going to be fixed. And in similar way, in civil engineering, there was a topic coined long back, a few decades back, called as structural optimization. What is structural optimization? So structural optimization means we wanted to reduce the weight of the structure, okay? Reduce the weight of a structure, and I will come to this, that why reduce the weight of a structure. Let us take an example first of all, then I will tell you, then it will be more clear that why structure weight has to be reduced. So coming to this area, structural optimization, and why it is required and how it came into the picture. So let us see structural optimization, or just a simple mechanical design. Suppose we have a beam here, okay, and we wanted to apply a load into this one P, and it is supported at two end, okay. Now, what is the condition that you get the maximum stiffness? What is the condition that you get the maximum stiffness? And when you talk about stiffness and so on, you directly focus on the shape or the size of this beam, okay, the shape or size of this beam. And shape and size directly refer to the amount of material used. So it means if you wanted to make more stiff, so we can increase the depth, we call it T. This we can increase. This also, the width of the beam can also be increased, okay. Length remains constant, length is constant, and you can keep on increasing the thickness. But up to how much extent? Up to where we can go? What is the maximum value at which we can go? So you can see that when we slowly increase the material amount, the weight is also going to be increased, and it has to happen in optimized value. If you do it in non-optimized value and we choose width larger than thickness and keep on increasing the amount of material, what is going to happen? The weight, self weight of the material will also increase. Self weight. The self weight of the material will also increase, and not only because of the applied load P, but also with respect to self load also, this will undergo a large sagging, or you can say large deflection. It means that increasing the amount of material is not the solution. Then what is the solution? The solution is to the solution is to use this material in an optimized way so that we get the minimum deflection. Okay. So with this problem, we create the problem of structural optimization, and we'll slowly see that how it will come to the mechanical engineering or design of machine component. We start from structural engineering. Okay, before that, what is structure actually? So this is very simple. You know this all things, structure and mechanism. Structure is something which has got 0 degree of freedom, and mechanism has got n degree of freedom. Okay. So if, for example, if you take a triangle, and you try to compute the degree of freedom using Grubler's law, you'll find degree of freedom is equal to 0. So it will not move, though all are pin joint. If you take all 3 pin joint, even though it will not move, it will not have a deflection or sagging or a kind of motion here, because the degree of freedom is 0. Contrary to this, if you take 4 joints like this, and fix these two, you will find that there is a large motion because degree of freedom is 1. So there is not much difference. The structure is same, joints, links are same. Only the numbers are going to change, which gives different degrees of freedom. The structure is something which has got 0 degree of freedom. Mechanism is something which has got 1, 2, 3, 4 degree of freedom. But the essence of both are going to be same. So that is why the similar methodology can be extended to mechanism or machine component. So that is why we entered into the area of civil engineering and see what is structural optimization. So here what is happening, we wanted to work out first of all in truss problem and see what is happening. So this is called as size optimization. The first kind of solution to this problem is called as size optimization. In size optimization, what is going to happen? You can see this as a truss here, which is shown here, and it has got identical members. Okay, there are different identical members, and out of these members, we wanted to find out which members take 0 load. Out of different members, which member take 0 load or is not loaded at all when it is situated like this, or which member takes less load, which member takes high load. So in the size optimization, what we do, we work about the cross section design. It means, suppose if we are taken a circular member, okay, circular bars which are used, or you can take L shape, which has been considered here. So you can take L shape or whatever shape is there, and you can decide what should be the cross section area, diameter, length, amount of material which can be deposited. So the member which is taking highest load should be more thick compared to the members which are taking 0 load or no load. Okay, 0 load or less load. So here after the optimization, we can see that these members, shown in the thick line, were taking the largest load, and that is why these are made with different cross section. So the size is different, the cross section size is different. So that is why it is called a size optimization problem, in which the objective function is to minimize the deflection, and the parameters on which the optimization will be carried out will be different members. Let us say how many members you can count here: 1, 2, 3, 4, 5, 6, 7, and so on. There are n number of members. For each member, the cross section, the diameter can be described as d1, d2 to dn. Correct? These are the things. So in optimization problem, we will define minimization of the deflection, the overall deflection, subject to and this deflection is a function of d1 to dn. Okay, because weight of these are contributing to the deflection. Subject to, you can put a constraint that it should be always greater than 0 and should be less than a particular amount which you wanted to fix here, and the length and all can also be put here. So that is how this can be. You can use sequential algorithm or any different kind of algorithms are available, constraint, non-constraint. So we can use any kind of problem solution methodology and solve this problem. So finally, we get different values of d1 to dn. So the parameters for which we do the optimization are d's. So we optimize for d's here. Okay, and the minimization function, the objective function is minimization of deflection, this deflection. So this problem type is called as size optimization. This is called as size optimization. Now coming to different type of optimization, which is called as shape optimization. In this, what is happening? Suppose we found that in some of the cross section, some of the beam, the circular area is circular holes are required. Now we wanted to know what should be the shape of, what can be the shape of these holes so that we get minimum or maximum deflection, minimum or maximum deflection. Deflection I have taken For an example, you can take any other parameter, deflection or stress or weight or whatever is there. So here, in this case, the size has to be found out. Shape was circular to circular only. It can be D1, it can be D2, or it can be anything. D's are changing, it means the shape is not changing, only the size is changing. And here what is happening, instead of taking a truss structure, we take a, it is called as monolithic structure. We take a monolithic structure and we make holes and try to know what should be the shape of these holes so that a desired quantity can be minimized or maximized based on the different shapes. So this problem becomes little bit complicated because a shape is comprising of different kind of you can say the curvatures and different kind of curve which can be added together to give a particular shape. So this is shape optimization problem in which we try to optimize the shape so that we get the minimum or maximum values. Okay. So here what I am using the term, please check here, optimizing the shape. Okay. So these parameters are optimized. We have to remember these terminologies because frequently we use these terminology. There are two terms involved in optimization. One is called as optimization and other one is maximization or minimization. So what is optimized and what is maximized or minimized? These are the objective functions. Objective function which is maximized or minimized, correct? And what is optimization? Optimization of the parameter. Optimization of the parameter. We don't optimize the objective function. We optimize the parameter to get a max or minimum value of objective function. For example, you wanted to increase the heat transfer from what you call from a cylinder. Okay, surface to volume effect is going to come. So you wanted to dissipate the heated object which is in cylindrical condition. We wanted to dissipate more heat from this one. So we need to find out what should be the volume and what should be the surface area. Okay, the mass is going to be fixed. Mass is going to be fixed. So the parameter in this problem will be to find out a value of H and D, correct? So parameter here will be H comma D and objective function will be delta H, let us say heat transfer. Okay. So heat transfer will be maximized and D and H will be optimized. So the parameters are optimized. Parameters are not maximized or minimized. Parameters are optimized and the objective function is maximized or minimized. This terminology need to be used very carefully. Otherwise, the person who is listening to you will understand that you are a very immature person in optimization. So optimization always talked about the values of the parameter which are optimized to give a max or min value of the objective function. So here the shape contours will be optimized to maximize the function, for example, deflection, stress, mass or any other thing. Okay. So this was shape optimization. Now coming to topology optimization. This is a relatively new area and which is very, we can say very cutting edge area nowadays, either in civil engineering or mechanical engineering design. And our topic of discussion will be topology optimization. What is topology optimization? So by definition, what is topology optimization? We'll see. By definition, topology optimization is something which helps to define the holes and connection. This definition is not available most of the time, so I thought it is. Let us write it. So what is topology optimization? Topology optimization is we have to define holes and connections. What is the meaning of this one? Holes and connection. So here we will define the whole material domain. Material domain will be first of all defined. What is defined then? If it is not defined, what is defined? So the given thing is, or the defined thing is given material domain. Material domain. What is material domain? So let us try to take the same problem. This is the area in which we wanted to distribute the material and this is a beam. Okay, wanted to distribute the material so that you get minimum deflection or whatever is the, let us say, minimum deflection. Now this whole amount of material is some let us say in kgs, some mass is there, and we can put either whole everywhere you can put this material, or you can wisely distribute the material so that you get the minimum amount of stress or deflection because of its self weight as well as the strength. Okay, so you have infinite ways to place the material, and while you place the material, we observe the holes, somewhere symmetric holes like this. You observe the symmetric holes. Okay, or we observe the connections. So here you can see that we have defined symmetric holes which may come because of the optimization. So these are the holes, and this will do what? Reduce the weight, and by reducing the weight, the deflection will also reduce. The self-loading is going to be reduced. So what is required here? We have to reduce the weight so that the deflection can also be reduced by self-loading. So we have to define where we wanted to make the holes, correct? Where we wanted to make the holes. At the same time, we have to define the connections. Connection means how, when the holes become larger, when these holes become larger, we have to find out how the connection is. The connection is like this, the material connection is like this or like that. It may emerge in this way, it may emerge in this kind of shape. Okay, where you can see something like this. Okay, this is the hole, and this kind of holes, and you get this all as filled one material, the shaded one is material. Now in this, the holes and connections are very well seen. So the problem to the designer is how to define that where is the material distribution, so that we can see distinct holes in this material domain and we can see distinct connections. So now in the shaded region, you can see the different holes, at the same time you can see the connection, which makes an entirely new and innovative shape for this particular problem. Okay, it gives innovative and new shape for this particular, and this is the support. Fine. So this can be in this way. So now you understood the value, the meaning of topology optimization. It is about defining the holes and defining the connections. So if you further reduce the amount of material to be used, then it may be something like this. For the same topology, it may be like this. It means two bars, one is like this and one is like this, and two more connections like this, for example. So it may be very thin structure of something like this. Okay, so here you may not observe holes, but what is much more observed is connection of these shape rods or bars, correct? So this is what is connection, or in the other perspective you can say the holes. So topology optimization definition is, it is about to define the holes and connection to maximize or minimize the objective functions. Now how is it different from shape and size optimization? In shape optimization, we already know the location of hole, we already know the connections, correct? Hole and connections are known, only the shape of the hole has to be obtained. While in the case of size optimization, it is much more restricted. The shape is also known, only the size of hole or size of the shape has to be defined. So size optimization is a very restricted optimization domain, wherein we don't get the maximum flexibility to save the material. While if you see to the third step of topology optimization, you have full freedom to define the shape and size and connections and whatnot for a particular material domain. The required one is only material domain and boundary conditions. These are the two things which are required. Boundary conditions. These are the two things which are required to start the topology optimization problem. So let us see the different methodologies. So methodology wise, if you come to this one, we have already discussed this all things. How do we do this? How we Suppose in this problem, in shape optimization, if you wanted to define, so the objective function will be what? Let us say deflection is the function of shape, and shape is function of parameters x1, x2 to xn. Different Bezier and B-spline curve can be defining these shapes. This is the objective function deflection, and then somewhere here you will calculate the mass into this one, okay, and then the parameters will be what? X1, x2 and so on. And if it is constraint subject to, you can give any min or maximum value, or you can define that the holes should not meet each other. It should not be connected so that two holes become one hole. So you can define that relation between x1 to xn is equal to some value of x1 to xn, so that the holes should not grow such a way so that it meets each other and become one hole. Okay, so this may be one of the condition. This may be one of the condition which can be defined or which can be left like that. Now let us see one by one. So coming to topology optimization, there are various you can say the methodology, and out of these two methodologies, the problem is classified in two ways: discrete topology optimization and continuum topology optimization. What are those? So in discrete means we define the truss structure of which comprises all the possible type of connections, out of which we define the optimum connection. So let us see that how this problem is done. You have to understand the physics of problem, then the things will be or can be defined in a very well way. For example, you wanted to make a beam. Again, since being a structural problem, we'll take beam problem. Now what is happening here? Let us say this is the beam, and this is the support. So we define support here, one support here and another support here. Fine. And in this beam we will define distinct points, let us say discrete points, which we can do. For example, these are the 2 points. Now in this, before topology optimization of this discrete structure, we will define all possible types of connections which can be there in this one. So we can connect it in this way. Let us say we can connect here, we can connect here, like this. We can connect here, we can connect here. So all the possible connections will be defined first of all. Then somebody may say, no, we'll connect in this way, connect in this way, connect from here to here, also possible, connect from here to here, this is also possible, and in the same way. So you can make different type of all the possibilities which are there in any type of optimization, any type of this. So you can make all the possibilities of connections. We'll define all connections. So after making all connections, like here in this problem it is made, first of all we'll make all possible connections. All possible connections. This is called as ground structure. Okay, all possible connections are made, and after that the optimization scheme is employed, which removes the structure which carries almost zero or minimum stress or load. Okay, so the members which carries maximum load will be remaining and others will be removed. So here you can see as per the definition, it is doing the topology optimization because we are still defining the holes and the connections. We are still trying to find out which are the optimum connection which defines the hole. So it is still valid. This is again, this is a topology optimization problem. But what is specific here? The size of the members remains same. Is not going to be changed. It is unchanged. Okay, it is same as it is. The size of the member remains unchanged. Now, one of the issue is there when you do the topology optimization also, and when you go for very high number of volume fraction, means you wanted to remove the maximum amount of material, even though we get the such kind of structure. So let me define it again. So suppose if you take something like this, and here we define this black as whole material, and after optimization you will find it at in this way, where this will be defined not like this, but a new kind of topology will be generated, and you will see how it will look like. So a new kind of topology will be generated. These are all published results. So this is a new kind of topology which may generate. Okay, just for example. So here you apply a load here P, and these are the two supports. So now here the question arises, what is the difference between, this is the example of continuum topology optimization. Continuum topology optimization, where we don't make a ground structure. There is no ground structure. No ground structure. So without ground structure, what is happening? The material itself define itself in different shape and then come towards this one. So what is the benefit here? We need not to define n number of ground structures. We need not to define it, and it automatically comes as a final structure. So that is why continuum topology optimization problem is largely utilized compared to this one. But the problem is the shape is a non-standard shape of the beams. So the manufacturing is difficult, as well as the, you can say, the analysis is further analysis difficult. While discrete optimization problem, you can see that always it has used the same similar type of standard bars here to develop the optimized structure. So the manufacturing is very easy. So that is why people take a discrete topology optimization problem also for multiple uses. Now we see another dimension of topology optimization. Let us pause it here, take a pause here, and come to another type of problem. There is something called as compliant mechanism. Many of you might be knowing, you might be aware of this kind of mechanism, which is called as compliant mechanism. It is related to a term called as compliance. What is compliance? Any idea? What is the meaning of this word? Please type so that I can see that you are aware of this. What is the meaning of this word in your mind? Compliance. What is the meaning of compliance? Please type in your chatting box. Any idea what is compliance? So in mechanical engineering, or you can say in the structural form, compliance is the degree of flexibility. Compliance is the degree of flexibility. So we can define the flexibility in terms of compliance. Okay, and the mechanism which is flexible is called as compliant mechanism, based on mechanism flexibility. So here the one which we are seeing, this is a engine, this is a plier. Okay, these all are mechanical example, and you can see the joints are there, and from the joint it produces the motion. Okay, from the joint these produces a motion, and these all are the example of rigid bodies. These are the example of rigid bodies which are considered here, and from the rigid body the joints are used to provide motion. Can't we think about some mechanism or some process through which there is no joint in the mechanism, and based on the flexibility or the compliance of the structure we develop such motions? So that research was also carried out, and people come across the similar thing without having any joint. These are again monolithic design. Monolithic means in one assembly itself, or you can say there is no assembly, in single part, monolithic, or you can say single part design. Single part design, the similar components are made. This is the plier. If you hold it from this direction, from this and this will clamp in this direction. And this is bistable mechanism. Bistable mechanism. Like switches, we normally see MCB switches, the side view, it moves up and come down. So either the switch, if I make it more properly, this is how our MCBs look like that, and this is the switch. Okay, either it stays to this position or you turn it down, it stays to this position. Am I right? This is how MCB will operate, or any switch you can say. This is an example of a switch. So either it goes to this direction or it comes to this direction, MCB. There is no stability in between. There is no stability in between. This is called as bistable mechanism. Bistable mechanism, either position number 1 or position number 2. So if you open any switch, you'll find lot of rigid bodies, spring motion, and so on, and multiple parts will be there which are assembled together to give this type of bistable mechanism. However, the same can be done through a compliant mechanism, and here is the example where you can. This is the switch. Either it stays in this condition or it stays to the opposite condition like this. So this is a compliant mechanism based switch by bistable mechanism. Let us see a few example. You can type this on YouTube, or you can see various example. And here you can see, I will just show this video so that quickly we'll go through this and see what is a compliant mechanism here. These are used in macro as well as micro. This is a bistable mechanism. And now you might have a good example of compliant mechanism. And this work was basically initiated in Brigham Young University, where various people like they have Professor Larry Howell. He have started working initially in the area of compliant mechanism, and they have full laboratory where they have shown different type of mechanisms, this clipper and so on, and you can see this functioning. And this is a good research area where people can employ their creativity to make monolithic structure without any joint. So now coming back to our topic. So this is again an application of optimization. We'll see how these different type of mechanism we just now see. So how do we do this? So there is a book by Professor Larry Howell on compliant mechanism. So you can see that book, and there are several chapters in which analytical solution to large deflection problem and non-linear problem is shown. And at chapter 9, I think, chapter 9 talk about compliant mechanism design, this particular methodology, which is edited by Professor Anupam Saxena. He is now in IIT Kanpur, and he was the student of Professor Larry Howell. Another fellow in India is Professor G.K. Anant Suresh, ISC Bangalore. He is working in the area of compliant mechanism, and Anupam Saxena is working in the area of compliant mechanism. Professor P.S. Gandhi in IIT Bombay also works in this area. So there are very few people in India who works in this particular area. So now here we'll see in this particular slide that how do we go for the design of compliant mechanism. So first of all, this is the ground structure prepared here in this figure, and you can see this whole structure is defined. First of all, there are different nodes and different elements, and we define load and output point. Load and output point. This is important here. Means we assume that from this point load will be employed, or the force will be employed is equal to 2 Newton, something is given, and output is coming out from this point, delta out. Okay, the out is coming from this point, and then in order to maximize this output, remember in the structural problem what we did in these problems, we try to minimize the deflection, okay, and you get this structure. What if you wanted to maximize a particular displacement from a particular point, and that will give you the view of compliant mechanism. So that if a force is employed in a particular direction, the maximized deflection will be obtained from a particular node or direction. So this is how the optimization will run. This is the function, general function. Minimize or maximize. It is minimize of stiffness here, which is a function of all x1, x2, x3, x4 here, subject to particular constants, and the sensitivity is required here. So there are different forms we'll see. So this is how, when the optimization is performed over this one, we find this kind of a structure where all the other elements are removed, the thin elements are removed, and finally we get this structure which is later manufactured using 3D printer mechanism. And here you can see if you applied load to this point, it will give the output from this point, maximum output from this point. And if you use the mirror image of both, it will become a compliant gripper. So you push from this side, okay, we push from this side and it will come closer to this side. Also, people have tried to find out some material which is called as negative Poisson ratio material. What is that negative Poisson ratio material? Let us see what is negative and how they have. Normally we know that if you stretch a sheet or a metal bar in this direction, if you employ the force in this direction, what will happen? It will compress in the transverse direction. Since the material amount mass is fixed, so when you stretch in this direction, it will be reduced in the width and elongated. It is like this. So, and here comes the theory of Poisson's ratio, which is the ratio of longitudinal versus transversional stress and so on. Now, negative Poisson ratio, what is this? Negative means if the same is employed, it will stretch to this direction as well as expand to the other direction. So that is negative Poisson ratio. It is not possible physically because of conservation of mass. So it is not possible, but if you make thin structure into this one, you get material which expands outward in all direction when it is stretched in one of the direction. So you can find out research papers. This is a famous research by Professor Ole Sigmund. in Technical University of Denmark. So these people have developed this kind of material which shows negative Poisson ratio, and expansion happened in both forms. Now coming back to the objective function, how to define the objective function. So there are two things defined: strain energy and mutual strain energy. So strain energy is nothing but half sigma u square, okay, stress, or u into compliance stress. This is strain energy, kx square you can say. So this is termed as compliance here. This is termed as compliance, which is reciprocal of stiffness. So if you have more compliance, it means it is more flexible and stiff, or it is compliance is simply flexibility. So it is flexibility which is opposite to this one. So we can form, for this mechanism problem, different objective functions can be formed based on strain energy stored, which is going to be obtained as compliance. So mutual strain energy into strain energy, and alpha is a parameter which moves from 0 to 1. Then again strain energy, and this can be specified. Then in other formulation, it is mechanical efficiency output by input, can be defined in this way, or further it can be simplified in this way. So there are different things, or we can define it in another way also. Input port means it is receiving the force, and from here it is giving the output, and this output is received through a spring. So here also you obtain a force. Here force equal to ks into x, and like that can be also defined. So you can see that this is how in a different way the formulation of this problem can be done, and the codes are available on MATLAB. The code for these problems are already available, and this is nothing but this is a simple application of optimization into these structures. Now coming to any question till now, shall we move to next section of this lecture? Any doubt or anything? Okay, let us move ahead. Now coming to topology optimization problem, we have seen this one, discrete structure, discrete topology. Now coming to continuum topology optimization from problem formulation. So this was initially given by Bendos and Kikuchi in 1998, and actually before that Bendos worked, and in 1995 he published a book on topology optimization, continuum structure or homogenized material distribution. So in 1995 itself the book has come on topology optimization, and the problem is something like this. We define the material domain omega, and we define the boundaries, supported boundaries, and we define the portion at which load is acting, okay, and there are some void which may be there, and this void helps us to find out volume fraction. We'll see later. So in a very simple manner we can understand the formulation as minimize the compliance, which is a parameter of x. So what is compliance? What we do here, we discretize this material into different finite elements, okay. So in this way, let us say that we are trying to minimize the find out the topology of a particular beam. We'll take the same example. So what we do here, we discretize it using finite element methods. So we discretize it into various forms, various elements, and for each element we define a parameter x. Now once you define it, we can place the material in some of the boxes and leave some of the boxes empty, and that will be the different type of function. Let me show you in a more proper way. So if this is the material domain, we can define it, we can discretize in various elements, and then we have various options to fill the material domain. So like that, we can, let us say, discretize it in very coarse, you can say, material elements. So this is done using discretization scheme in FEM. And then after that, here you define that these are the nodes coming to in FEM terminologies. These are the nodes here, defined nodes. And then you can define the material as, you can define it, material is here, material is here, material is here, and so on. So now you got a rough sketch of the beam which may look like. You can define it in this. So you have a very large number of possibilities. You can define it in this way. We can define the material in this way also. Somebody may say do material presence can, so you can define it in this way. One can define in other way. Okay. So there are infinite possibilities, not infinite, it is finite, but large possibility of defining the beam in the different way. So what is the problem here? Can you find out what is the parameter here? So let us define the beam in this way. Okay, half beam only, few or the element only empty. Like that, what we can define here, the problem is, for each element we define a parameter x. For each element we define a parameter x. Okay, for each. So how many x will be defined? 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4. So there are 24 elements here. So 24x will be defined. x1 to x24. 24x can be defined. Now what is the meaning of this? These x can be 0 or 1. We can define these x with the binomial values. Either it can be 0, these x can be 0, or these x can be 1. These are the values. Values of x can be 0 or 1. Now when you say it is 0, it means there is no material. So for example, if you write this x1, this is x2, this is x1, this is x2, this is x3, x4, x5, x6, 7, 8, 9. So from 1, 7, 8, 9 and so on. So 7, 8, 9, 10, 11, 12, 13, and again 6, 19. So this is how the number of x will vary. Now you can define the material as x1 is equal to 1. So we put material here x1 1, x1 is equal to 1, x2 equal to 1. You can say x19 is 1 and x24 is 1. And similar way you can, wherever you say 1, we will put the material, and wherever you say it is 0, we don't put the material. So at the end, based on 0 and 1, we can define the distribution of material. This seems to be very coarse. If you increase the number of these parameters, x means more fine element, you will go with a very fine smooth structure here. Okay, so that depends on this one. Now can we define the objective function compliance value kx square? We can define kx square here, where k is the stiffness matrix, and how it is done, let us see. So in kx square, what we will do in this particular formulation, now you understood the value of x, and x is the parameter which we will try to optimize to get the minimum compliance or maximum compliance value. So how do we optimize x? So here k is the stiffness matrix, d is the nodal deflection of a particular element, and x is the parameter. Okay, so x has to be defined 1 or 0, and for each element it is computing the strain value kx square, kd square here. For each element, d is the deflection matrix, nodal deflection. So for each element it is finding out the deflection value and multiplied by this particular stiffness matrix. So you generate the strain energy which is stored, strain energy stored here, into x value. If x is 0, it is going to contribute nothing because there is no material. If x is equal to 1, it is going to contribute into this one. It means there is a material, so that we can take account the value of strain energy. So that is how infinite, or you can say large number of possibilities will be there for defining the material shape here. Material shape, or you can say the topology. Now subject to, if you add all the 24 or all the number of x, what you will get? You will get total number of element. Okay. And for each element, if you know the volume, elemental volume, if you multiply, you get the overall volume. Overall volume here. Sigma x into NE is equal to overall volume. Now, while defining the topology optimization problem, we have to define another parameter which is called as volume fraction F. Volume fraction F means out of this 100% material domain, what is the percentage of material which you would like to use to define the material? Let us say 50%. It means that if this volume is 100, so only 50% of this volume should be utilized to give a topology, correct? So it means the mass will be reduced by 50% for this particular object. Now this is used by various practitioners nowadays using various softwares to reduce the mass of mechanical elements. So that case study is also there with us. So that is how we get the reduced value of the mass here. Fine. Now coming to another point, this is what total volume here, which is defined with respect to x value, and total overall volume of this particular, like this is 100 and this is 50, so it should not cross a particular value. So Vx will be calculated based on elemental volume plus all the x, sigma x, I to n. So like that, we can compute what is the volume, and it should be divided by f so that you get the maximum, multiplied by f so that you get the maximum value of this one. So now this is what is the constraint, and k d into f will play here. It is, though it is written in constraint, but it will come into the objective function because the moment we applied the load, force vector is known, k is known, okay, and then we can find out the deflection matrix here. And x value is from 0 to 1. Here x mean is employed, otherwise the problem will be difficult to solve through MATLAB. It goes 1 by 0 and so on. So minimum value 0.001 equivalent to 0 can be considered. So that is how the topology optimization problem is defined. And there are other methodologies also, like evolutionary structural optimization or bidirection. So this is called as ESO and BESO. So this is also called as hard kill method. Let us see what is that. Hard kill method. In this method, what happens? We discretize the material into different elements, in finite elements only. This all works on the finite element structure, finite element base only. So one must know FEM very well. So for each element, we give a sensitivity number alpha, as we have given this one, and then one by one each element or group of elements are removed from this one, and this is called as hard kill method. We kill the elements one by one and see what is the compliance or the objective function coming, and wherever you get the maximized one, we'll stop it there. So that is how this is the method. Once what happened, when I was new in this area, I tried to do it using a common methodology. What I tried to did, I thought that instead of using optimization, why don't I try all the combinations? So we have made 10 cross 10 elements. So like this, there are 10 elements, 1, 2, and so on. So there are total 10 in this, 10 in this direction. And total a big beam is discretized into 100 elements. 100 elements like this. And with 100 element, I was not getting a very smooth, what you call, boundaries, but though it was working pixel wise, it was okay to start with. And then for each I have defined x value, and then we try to find out the strength or compliance value based on this x, and I have used for loop It means 10 for loops I have used, 10 over 10. It means for each combination, this is material, there is no material, here material. So for each element, all the combinations of this 100 element in binary fashion 1 and 0 was tried. I hope you understand. So it's a crude method in which we try to see that how the compliance will vary if I try to do it one by one. I put material here, then I put material in one way. It means all the combination of topology can be seen, and then we can find out where is the compliance minimum, and that's all. At that time, I was not that much familiar with optimization, and I was trying to run away from the optimization and do it in this way. And I thought, "ठीक है, I have computer, the computer will do anyway. Why to learn optimization? And just check it for all the possible combination, and that's all." And then I ran the MATLAB, and it was supposed to store the value in a notepad. Okay. And then morning I started this code. Evening in the night I checked the code was running. Then again next morning I thought result will come, but again I saw the code is running. Then next second day night also I checked the code was running, and this keep on happening for 3 days. 3 days I could somehow I could stop myself to stop the code. But after 3 days, I was not patient enough to see that code is running. So I terminate the code and try to see how many time is required to run one set of iteration. So I found some minutes, some seconds required here. Then I saw what are the different number of combinations here, and then I calculated. You will be surprised to know that how many time, what is the time duration for each step. Around 6 seconds was required, something like that. So when I calculated that when my code is going to be finished, so it gives a data which is in month. So in few month, in some 100 or 200 days, this code has to run to give the optimum solution. And this was for 10 cross 10. If I go for 100 cross 100, like a realistic value in which we get the smooth value of the surface, if the system was telling that it requires 500 years, you will not believe, 500, 600 or 300 years. So I thought I could not, that much time will not be available for me to finish the PhD. So I have to learn optimization. So that was the conclusion. And when you run this problem through optimization, it will not even take 1 minute, less than 1 minute, to do a job which requires to be done by several months. Okay, so that is the beauty of optimization, where in the problem or different combination which will be tested in several months will be done in few seconds only. So this was a hard kill method, where we can see the sensitivity of each element one by one, and then we can go for that. Then now coming to level set method, here what is happening? There are two surfaces which are defined. One surface is flat, and the other surface has got different 3D contours, 3D shapes and contours above, just like waves in sea or something. And then we cut this surface by this flat surface, so we get different type of shape. So these two methods are there, and we set the level here, level set here. This is a Japanese method. This is very complicated and nowadays largely utilized. So this is how it generates the topology. So there are three important methods. One is structural isometric material with penalization method. This is called as SIM. And the other one is ESO, BSO and level set method. Now in this, what is penalization? You can see x to the power p. So penalization means this optimization problem is not binary problem. This is a continuous problem where from 1 to 0, any value will be assigned to x. Any value will be assigned to x. It can be 1, it can be 0.5, it can be 0.6, 0.7, 0.8 or anything, which has to be go back to the material and define the material. And then what happens? The code generates gray code. Okay, this optimization code generate grayscale. As you can see, grayscale here available. So it's a grayscale image which is coming. So there is a problem that how to remove this grayscale. For removing the grayscale, the idea given by the researcher was to use penalization. So for example, if X value is something and if you employ penalization, this is going to be reduced. So it is going to be reduced like this. So anything which is near to 0.3 will be considered as 1, 0.7 considered as 1, and below anything 0.7 is considered as 0. So this is penalization. When x to the power of number, if you put here x to the power n, then it will give a penalization effect. It means that any power larger than any data value 0 to 1 can be grouped into two groups. One is 1, the other group will be 0. So normally this p is kept as 3 for general application problem. So if you cube the x value, it is going. Now there are different filters available which filter grayscale and all. Now there are various problems which are coming into this topology optimization. What are those problems? Let us see, and then we'll finish this one. Leaving the problem, I will come to the realistic example. This is the realistic example of topology optimization. This is AVB robot, and I will tell you that how we have performed topology optimization and what are the different effects which are coming. So this is ABB IRB 120 robot. ABB IRB. Okay, this is the technical specification of this robot. And yeah, ABB IRB 120. The payload is around 3 kg and stretch is 60 to 70 centimeters. This reach is around 70 centimeters. And we can employ a load of 3 kg here. So here there are different links which are considered. You can see link 1, link 2, link 3, link 4, link 5 and link 6. So we wanted to reduce the mass of these links. Why do we wanted to reduce the mass of these links? Because if we take a reduced mass, what will happen? What is the benefit we are going to get if we reduce the mass of a mechanical element? So let us take an example to understand this issue. So suppose if we have a reduced mass, then what is going to be reduced here? As we have seen in the self-loading, the same effect is going to come here. So let us say that there is a link here which is rotating with respect to this axis. It is rotating with omega velocity. So what are the forces that are going to come? What are the forces? One force is payload here, which is P. Okay. The other force is, let us say, CG is lying here. So this is the self-weight W. When it rotates, the centrifugal force is going to come here. Okay. So FCG is also going to act here from this CG point. So there are three loads actively working on this particular area. Now W and FCG is dependent on what? W and FCG. So W is going to be dependent on self-weight, and FCG is going to be dependent on alpha and omega and weight. So out of this, you can see weight is common. If you reduce the weight, self-weight, if you reduce the self-weight of this link, what will happen? These two components are going to be down. When these two are going to be down, then what will happen? The inertial force is also reduced. Inertial force will be also reduced. And the weight will be reduced, inertial force will be reduced. Now what is the function of inertial? What is the effect of inertial load here? Inertial load gives unbalancing. If high inertia unbalancing or inertial load is high, unbalancing will be large. And then in that way, if unbalancing is large, it will be inaccurate. Let us see in physical way. If we take this big rod and try to rotate with a high velocity and it has to stop at 30 degree, what will you face here? This fellow will not stop at 30 but try to move ahead 30 degree. So we have to put mechanical brakes here so that it can stop this fellow immediately. And when it stops, it vibrates because having high inertia. It vibrates and then stop. So these are the effect of larger inertia value. Okay, and that is because of high self weight. So if the self weight is reduced somehow, the accuracy of these robotic system or moving element can be increased. At the same time, the torque required to operate these links will be also reduced if the inertial loads are going to be reduced. As you know, tau equal to F into distance. So the forces, this P is fixed, however W can be reduced, and when W is reduced, this torque W into D will be also reduced, and that is how you can see that less torque will be required by the motor to run this link. So that is why the objective was to reduce the size, reduce the mass of these links, so that we can reduce the torque employed from this motor, and the performance will be much more accurate. So with that objective, we have first of all run through. Now this is a very complicated structure, and though we could have find out the FBD of each link, free body diagram of each link manually, and do it analytically, and this force and dynamic analysis, we can do it, but we have taken the help of software Adams software, and for each link, let us say joint 2 and joint 3, we have simulated this robot and find out what is the torque required from one point to other point, moving from one trajectory to other trajectory. And by this way, we come to know the torque required and the forces acting over that, which will be required to do the topology optimization. So here, the fixed support is given, torque is employed, and then with the boundary condition known, you can operate this thing in topology optimization. So we have used software OptiStruct, Altair OptiStruct software to do the topology optimization. There are various software now. When we started working into this one, hardly there was no software to do the topology optimization. But nowadays, almost all solid CAD software give you the possibility of topology optimization. Everywhere it is available. You need not even go with MATLAB and so on. Now, for every values of volume fraction, we can see the topology in this way, and we can see the deflection and stress values. So based on the desired values of deflection and stress, we can select any particular volume fraction. So 0.2 means this is the solid material domain. This is a full material domain. And 0.2 means 80% of the material will be removed. You get a very light structure. So only 0.2% of or 20% of the weight will be there with me. But the deflection will be large. You can see it is deflected and stress will be also large. With 0.3, you can see it is little bit thick. Deflection and stress values are much improved. 0.4, 0.5, 0.6. So you can see that it is slowly going towards the solid region from one to another. And then you can see the deflection and stress values are also being improved. So with topology optimization, we can do what? We can reduce the mass, we can reduce the torque required, and we can reduce the you can see the uncertainties or the error of the moving system. So in this session, we have started with the beginning. We have seen the different type of topology optimization schemes, and then we have seen the compliant mechanism, their applications, and at the end we have seen how topology optimization method is used for a mechanical system, and what are the software and other methodologies which are going to help us to generate an optimum topology. So with this, I close this particular session. Any question you can type on note this chatting. I'll be happy to answer. Otherwise, we'll close the session. Yes, any question from participant side? Yeah.
Hello, participants. Sir has completed his session. Any query, please? He has explained in a very good afternoon to all of you. This is Gurmeet Singh again. So I first of all thank Dr. Asharjee for sharing this precious knowledge with us in the field of optimization of robotic design. So I again thanks all the organizers and all the participants for being here continuously, and जो आपको यहाँ पर जो नॉलेज आपने शेयर की है ये हम ऐसी knowledge, it's not easy for us to get at one platform. So different presenters, all the presenters, what they have presented here is of immense importance. So I thank you again. Thanks all. I hand over
Thank you.
please continue. There is validity function. And please be there for validity function, and it will continue. Thanks all.
Thank you very much.
Dear participants, please see in the chat box that there is a feedback link, and validity function will start at 1:30. So please continue. हाँ सर, नहीं अभी तो सर ज्वाइन नहीं किए ना।